To make GANs actually work really well, it's important to choose a good overall architecture. If we have a very simple task, like generating 28 by 28 pixel images of handwritten digits from the MNIST dataset, we can get away with a fully connected architecture. In the fully connected architecture, all of the interactions between layers consist of matrix multiplication by weight matrices. There's no convolution, there's no recurrence. The most important design consideration for this architecture is to make sure that both the generator and the discriminator have at least one hidden layer. That ensures that both models have the universal approximator property and can represent any probability distribution if given enough hidden units. For the hidden units, many activation functions will work, but leaky ReLUs are especially popular. Leaky ReLUs help to make sure that the gradient can flow through the entire architecture. That's an important consideration for any machine learning model, but it's even more important for GANs, because the only way the generator can learn is to receive a gradient from the discriminator. A popular choice for the output of the generator is the hyperbolic tangent activation function. This means that your data should be scaled to the interval ranging from -1 to +1. Finally, for most versions of GANs, the output of the discriminator needs to be a probability. To enforce that constraint, we use a sigmoid unit as the output. GANs are different from many other machine learning models because they require running two optimization algorithms simultaneously. We define a loss for the generator and a loss for the discriminator. Then we use one optimizer to minimize the loss for the discriminator, while we simultaneously use another optimizer to minimize the loss for the generator. Atom is a good choice for the optimizer. This is one of the design choices from the DC GAN architecture, developed by Indico and Facebook. To set up the discriminator loss, recall that we want to train the discriminator to output values near 1 for real data and near 0 for fake data. This is just like training a regular classifier, in terms of the loss function we'll use. A lot of the time, people make mistakes trying to implement their own loss function. You want to remember that this is just a sigmoid cross-entropy loss, like you've seen before, and implement it the same way as in other classifiers. One place where people often make a mistake is they forget to use the numerically stable version of cross-entropy, where the loss is computed using the logits. The logits are the values produced by the discriminator right before the sigmoid. If you use the probability values that come out of the sigmoid, there can be problems with rounding error when the sigmoid is near 0 or 1. One GAN-specific trick is to multiply the 0 or 1 labels by a number that is just a little bit smaller than 1, so that you replace labels of 1 with labels of, for example, 0.9, and keep the 0 labels at 0. This is a GAN-specific version of the label smoothing strategy used to regularize normal classifiers. It helps the discriminator to generalize better and avoid learning to make extreme predictions when extrapolating. For the generator loss, you want to set up another cross-entropy loss, but with the labels flipped. In other words, the generator will maximize the log probability of the wrong labels. A lot of people like to use -d loss as the expression for G loss. It's very intuitive because it corresponds to having the generator maximize the loss for the discriminator. We even used that loss for a visualization earlier in this course. But it doesn't work very well in practice, and we don't actually recommend that you implement it for real. A lot of people like to use -d loss as the expression for G loss. That's very intuitive because it corresponds to having the generator maximize the discriminator's loss. We even used that loss for a visualization earlier in this course, but it doesn't work very well in practice, and we don't recommend actually implementing it for real, because the gradient of D loss is 0 whenever the discriminator is winning. Using -d loss as a loss for G forces the generator to maximize a cross-entropy. We really want both players to minimize a cross-entropy. Minimizing a cross-entropy works very well in practice because the derivative of the cross-entropy function is always non-zero whenever the cross-entropy is not minimized. So the losing player always gets gradient. That means it's much better for the generator to minimize a cross-entropy with the labels flipped, rather than maximizing the discriminator's cross-entropy. There are lots of other options for D loss and G loss. New GAN papers are coming out constantly, and many of them propose new losses. It will take some time to see which ones end up working the best for the most people. So far, everything we have discussed applies to almost every GAN. Now let's look at what we need to do to scale GANs up to large images. To scale up classifiers to work on large images, we use convolutional networks. Convolutional networks replace some of the matrix multiplies in normal neural networks with convolutions. We can also replace the matrix multiplies in GANs with convolutions. For the input to the GAN generator, we usually use a random vector z. A mini-batch of these vectors forms a matrix. The problem is, a convolution expects its mini-batch to be a 4D tensor, with one axis for different examples in the mini-batch, one axis for the different feature maps, and then the width and height axes. To get the random input into this format, we have to use a reshape op near the start of the generator. For example, we might transform a mini-batch of vectors that each contain 1,000 entries into a stack of 10 feature maps that are each size 10 by 10. Usually, convolutional nets change the shape of the feature maps as we move through the network. The input to a convolutional net is a very tall and wide image with just 3 feature maps, the red, green, and blue color channels. After applying convolution and pooling several times, we end up with very short and narrow feature maps. That's all what happens when we use a classifier convolutional net. When we use a convolutional net as a generator net, most researchers think we probably want to do the opposite. We want to start off with a small feature map and expand it to a wide and tall image. To do this, we need to have an op that can increase the width and the height of feature maps at every layer. The DCGAN project introduced the idea of increasing the size of the feature maps just by using convolution transpose ops with stride greater than 1. This just means that when we compute the convolution, every time we move the convolution kernel by 1 pixel in the input map, we move it by 2 pixels or some other larger number of pixels in the output map. Finally, you really want to use batch normalization, or one of the many follow-up methods based on batch normalization, in most layers of the network. The DCGAN authors recommend using batch normalization on every layer except the output layer of the generator and the input layer of the discriminator. They also apply batch norm to all the real data in one mini-batch, then apply batch normalization separately to another mini-batch containing all the generated samples. That's a little bit weird from a theoretical point of view, because it means we use a different discriminator function based on different batch statistics for real data than we use for generated data. Despite being a little bit weird, it seems to work well in practice. You can read about a few different alternative normalization strategies that are more theoretically straightforward in an OpenAI paper called Improved Techniques for Training GANs. Overall, this recipe of using convolution transpose, batch normalization, atom, and cross-entropy losses with label smoothing works fairly well in practice.